Alright, in this video we are going to look at areas bound by polar curves. So to start out, to review an area of a sector. So back in geometry, you set up proportions. So you had your partial angle over your whole angle. So often you did theta over 360, but because we're in radians, we have theta over 2 pi. 2 pi is the angle all the way around the circle, theta is the angle of your sector. A is the area of the sector we want, then area of a whole circle is pi r squared. Well, if we multiply the pi r squared over, the pi's wipe out, and we get 1/2 theta r squared. So that's the general form of finding an area of any sector of a circle. Well, say we wanted to find this area. Well, it's not a circle, but imagine we split it up into things that were almost sectors. And imagine we made those delta thetas, the angle in there, the little bit of change in angle, imagine we had that approach 0. And in other words, the number of sectors went to infinity, just like we did with Riemann sums with areas under curves. Well, as that delta theta goes to 0, these two radii links will approach the same value. So therefore, it'll approach the same setup as our area of a sector, 1/2 theta r squared. So the theta for us becomes the delta theta. So that's that here. We got the 1/2, and then our r is some function of theta, and that's being squared. So this right here, the starred thing, is something you want to make sure you have written down. The rest of the stuff, remember, it's up to you if you wanted to write it down. I'll probably go faster than you have time to write it down. If you want, you'll have reference to these videos, and you can just open it back up when if you get stuck on a problem. But do write down that starred part. So our area of any polar curve is just the bounds, 1/2, the radius function squared d theta. So here is an example. So we got 3 cos theta plus 1. So we always need to figure out what is the range, or what is the values on our integral. So if we put in 0 for cos, that'd give us 1. 1 plus 1 is 2. 2 times 3 is 6. So we're starting right here. This is our point when theta is 0. If you put in pi over 2, we would get 0. Plus 1 is 1. 1 times 3 is 3. So this here becomes our pi over 2 point. If you put in negative, or if you put in pi, we get -1, so that gives us 0, so that's our pi point. Then this would be our 3 pi over 2, and that's our 2 pi. So it takes a full 2 pi to enclose it. It will not always be 0 to 2 pi, that's why you have to go through and think of that. Now, we'll show you some other ways that you can work with that when it's not as nice, when we see some other questions. But we got our 1/2, we've got our radius squared, and we got our d theta going 0 to 2 pi. So we can pull that 3 out, but really it's being squared, so we're pulling a 9 out. That's how we get the 9/2. And if we FOIL out the cos plus 1, we get cos squared theta plus 2 cos theta plus 1. Now, we've got to go back to a few units ago when we're doing an antiderivative and we have cos squared or sine squared. If you don't remember our replacements for those, you might want to write down the 2 starred things. So cos squared theta, we replaced with 1/2 plus 1/2 cos 2 theta, and that came from our double angle formula below. So this bottom part's just showing you the derivation of it. You don't have to write that down, just write the 2 formulas we had. And then the sine squared theta also came from the double angle for cos, but that one had the minus in it. So because we have a squared for our radius, we'll have a lot of squared trig functions, so we'll have to use these a decent amount in these problems. So we can replace the cos squared theta with this one here. So the 1/2 will combine with the 1 to give us 3/2, and then we'll have the 1/2 cos 2 theta still, and the 2 cos theta. Now remember when we did these, technically this is a u substitution here. You let 2 theta equal u. So when you do your du, you would get 2 d theta, and you'd have to multiply by 1/2. So if you just remember that happens, you won't have to do the u substitution each time. So our antiderivative has a times 1/2 out front to give us the 4th, and antiderivative cos is sine. Antiderivative cos is sine, and if it's a constant, we get a theta in there. So then we fill in the 2 pi and the 0. So 2 pi would give us 4 pi here, so that's just 0, that's gone. Sine of 2 pi, that's just 0, so that's gone. And then 2 pi times this is going to give us 3 pi. And then the zeros will end up wiping everything out, because we'll get sines of 0. So we just have 3 pi times 9/2, which gives us 27 pi over 2. And that represents the area bound by the polar curve. Well, say we had this graph here. This is coming from 3 cos 3 theta. Now remember, each of these, you can get the graph just by doing graph entry edit on a graphs page and putting in a polar equation. Remember, you have to put theta in. It's with the pi button. And you could always do graph trace also to get an idea of where the things are. I think it's always helpful to think when theta is 0. Well, if you put 0 in for theta, cos of theta is 1, we get 3. So this 0, comma 3 would be our point right here. Now 0 meaning the, or sorry, 3, this 0 is the angle and 3 is the radius in this case. So for this loop here, we're going to go one way in a positive direction and one way in a negative direction. So when we set this equal to 0, we want to see what values are we at a radius of 0 there. So if we divide by 3, then cos is going to be equal to 0 at things like pi over 2, 3 pi over 2, but then also going the negative direction, negative pi over 2. And we had thought about here, okay, we got to go one in a positive and one in a negative, so we'll use the pi over 2 and the negative pi over 2. So that'll give us negative pi over 6 to pi over 6. So that's saying negative pi over 6 to pi over 6 is 1 petal. So we'll have to multiply it by 3 because there's 3 total petals. So that's the 3 petals, 1/2 our radius squared d theta, and we're going negative pi over 6 to pi over 6. If we can pull out the 3 squared and put it out here with the other stuff to give us 27 over 2. Well, this is just cos squared 3 theta. So we'll use our squared formula. So we have 1/2 plus 1/2, and then this always gets doubled. That's why we have the 6 theta there. So all that's going to happen now is when we do the antiderivative, we'll have a 1/6 come out there. So we'll get 1/2 theta. We'll have a 1/12 sine 6 theta. When we put in the pi over 6, we'll get pi over 12. This will give us pi on the inside, and sine of pi is 0. That's why that's gone. Then when we put in the negative pi over 6, we get the negative pi over 12. This will give us negative pi in here, which is also 0. Minus a minus, that becomes a plus pi over 6 when you put them together. And pi over 6 times that will give us 27 pi over 12, which reduces to 9 pi over 4. So if you have multiple petals, just do one petal. Make sure you're doing where the petal starts and where the petal ends on your integral values. So the last type of thing we'll look at in this video is finding the area of a limacon. So this limacon, it loops into itself. So if we want to find the area, this shaded area here, we have to do this part here, which does not include the excluded part, the little part, and then subtract off the little part. So those intersections there where the full part and the little loop are all meeting are all when the radius is 0. So if we take this and set it equal to 0, we could add the 2 cos theta over, divide by 2, and we get cos is square root of 2 over 2. Cos is positive in first and fourth quadrants, so we could have things like pi over 4, 7 pi over 4, or if we went in the negative direction each of those, this is fourth quadrant and this is first quadrant here. So I think it's always helpful to think about when theta is 0. Well, cos of 0 is 1, so that would be square root of 2 minus 2. Square root of 2 is like 1.4 minus 2, so that would give us a negative. So this point right here is our 0 angle and the negative radius. So that's where we're starting. So that means our little loop, the values for it must be on either side of 0, so it should be the first thing positive and negative on either side of 0. So we'll use the negative pi over 4 and the pi over 4 for the little loop. So basically, this is negative pi over 4 going backwards, and that's pi over 4 going this way, or vice versa. But then what that means is the big loop is starting at pi over 4. And then it must finish at the next value of theta, which would be the 7 pi over 4. Okay, because 7 pi over 4 is essentially the same spot on the unit circle as the negative pi over 4. But we need it to be a continuous loop, so that's why it's pi over 4 to 7 pi over 4. So little loop goes negative pi over 4 to pi over 4. Big loop goes pi over 4 to 7 pi over 4. So our setup would look something like this. In the first part here, notice it's the same equation for both, but this is our big loop. Okay, and this includes everything. And then we subtract off the negative pi over 4 to pi over 4 that we said for the little loop. And the remaining part gives us the shaded area. So the squaring out and everything is going to be the same for both. So I'll just show it for one of them. So we get 2 minus 4 square root of 2 cos theta plus 4 cos squared theta when we multiply it all out. We're going to have to do our substitution here with the cos squared theta, but it's going to get multiplied by 4. So remember, this is going to be 1/2 plus 1/2 cos 2 theta. When you distribute the 4, the half times 4 will give you a 2, which combines with this 2 to give us 4. And then the 1/2 cos 2 theta will get multiplied by 4 to give us a 2 cos 2 theta. And we'll again have that for both of them. So what I did here is I just showed the antiderivative of one of them. So here's our antiderivative. This got multiplied by 1/2 out front, which is sine 2 theta. And then it's the same for the other one, and we're just putting in different values. So what I would like you to do, a question's going to pop up in a second, but I would like you to sub in these values and see what it gives you and enter your answer in the question that pops up in a second. All right, so when we subbed in, we should have got 7 pi 4 negative 1 minus parenthesis pi negative 4 1. Okay, pi negative 4 1 minus parenthesis negative pi 4 and negative 1. And when we distribute our negatives, we get 6 pi plus 6, 2 pi minus 6. Distribute your negative 1/2 and combine them and you get 2 pi plus 6. All right, and that's it for this video on area bound by a polar curve.